One of the basic ideas in all of graph theory is connectivity. In some ways, it's one of the ways you probably would have gone about inventing the basics of graph theory just from thinking about questions of connectivity. It comes up all the time. Very simple things. You can imagine just any kind of electrical circuit. You want to know if you actually have electricity, you actually have a connection from one to another. And this is taking this notion of adjacency and kind of piecing it together. Now, algorithmically, if you want to compute whether two vertices in a graph are adjacent, this is not so hard to do. But you kind of want to implement, at least most of the time, you implement this by thinking about how you would do it yourself. Almost like trying to solve a maze, you kind of take your finger and you move it along the graph and you see if you can find a connected path from the start to the end. This perhaps simplest algorithm for doing this is pretty well known. I'm hoping that most students in this class have seen it before, but I'll do it again. I'll do it in code here. The algorithm is depth first search. And really, if I was going to present depth first search, the first way I like to think of it is as a generalization of tree traversal. Right? So usually if you have a tree, many tree traversal algorithms are written recursively. And you start at the root. The idea is that I'm going to traverse each of the children, but from each of the children, I'm going to recursively do another search, right? So first I go here, then I'm going to search this whole tree recursively, right? First I went here, second I go here, then recursively search this whole tree. And now where this goes wrong with a graph is that you have cycles, right? So if you have a cycle, then you may come back to yourself, in which case you don't just want to do this recursively. And also, if you're doing this in Python, probably you shouldn't be doing it recursively then either. If possible, it's often best to kind of remove recursion. But the idea is the same, is that I have a vertex, I'm at a particular vertex, I have a bunch of neighbors, and I'm going to go to a neighbor, and then I'm going to continue my search. Now, I have to be extra careful not to repeat myself, right? Because I could end up searching around in a cycle forever and never going in some other direction that I needed to go in. So I need to keep around a data structure that tells me at least where I've been before. But other than that, that's going to be it. And so rather than doing it recursively, I'm going to use a stack. Remember that any recursive algorithm is really just using the call stack as a separate data structures. So if I just have my own stack, I can just do this manually. And so let me pull up a window with some code here. And so I imported the graph that we implemented in the other video, and I'm going to write this function. I'm not going to write it as a method on the graph. You can imagine that might seem like a good thing to do, but what's cool about a lot of these search algorithms is that they only require the public interface of the graph. I just need to be able to traverse. I need to be able to look at a vertex and get to the neighbors, and that's all in the public interface. So I don't need much. So here's the idea. I am going to make a stack. And I guess this stack, in Python, the easiest way to make a stack is you just make a list. This traversal, I should also think about what it's going to return. You see, if I look at the paths I actually took, since I'm never going to loop back into a cycle, there's actually a tree that's formed. It's called the depth first search tree. And I'm going to implement the tree in this sort of funny way. I'm going to write it as a dictionary. And it's going to be a rooted tree, so it's rooted at the vertex that I'm starting from. And from there, I'm going to, every other vertex other than the root that I visit in this search, it came from somewhere, right? And it has that's the unique parent in the tree. And so by having a dictionary that maps vertices to their parents, it's a representation of a tree. It's maybe opposite to many of the trees you're used to thinking about, at least for search data structures, because the arrows all point up the tree towards the root rather than from the root down. And so to find a path to V, we can actually just follow parent to parent all the way up to V. So any vertex that can be connected by a path to V, we're going to find a path that will be in this tree. So this tree is going to give us, in some sense, an encoding of a path for every single vertex that can be reached from V. So there's a lot of stuff in here. All right, so I'm going to keep this stack of things to visit, and what I'll put on the stack are edges. So the idea is every time I have some edges that I care about, that I would like to visit, I'm going to put all those edges onto the stack, and every time I pop one off the stack, I'm going to look to see if it goes somewhere I've already been, and if not, I'm going to go there. Okay, so, and I'm just going to keep going until the stack is empty. So this is how you loop until stack is empty, and I'm going to pull the first edge off the stack, so AB equals visit dot pop. Okay. All right. Now this won't even get started though because there's nothing to visit even to start from. So I kind of need to beam myself in from outer space and land at vertex V. And the way I'll do this is I'll just put a kind of a fake edge here that goes from nowhere to V as the first edge to visit. And that way, the first time through, I'll get this. I'll end up at V. It will mean that I may end up with one extra entry in the tree, which is from V to none, right? Because I'm going to have something like tree of B equals A. That is, I got to B from A. That is, if I haven't already visited it. So I have to check that. So if I visited it, then it will already be in the tree. So, if B is not in the tree, then I'm going to visit it. And not only am I going to visit it, I'm going to take all the edges coming out of B, and I'm going to look at those to possibly visit as well. So I can do this like for C in G dot neighbors of B. So I loop over all these neighbors. Oops. And I'm going to add each one to the stack of edges to possibly traverse. So that looks like this, right? To visit, if I want to push onto a stack, if it's just stack is just a list, that means appending. So I'm going to append to the list the edge BC. Okay, so I'm just going to put them in as ordered pairs here. Okay, so I don't know if this works yet, but let's just see. Oh, I should at least return something too, and I'm going to return the tree. All right, I'm doing this from memory, so I probably messed it up, which is good because then we'll give you a chance to kind of think about it, find my errors, and then hopefully I'll find them too before the video's up. But if not, then you'll have the added satisfaction of having found the errors that I couldn't find. But I think I'm going to get them. Let's see. All right, again, let's fence this in. Right, it was important that I did this on our graph because it means that the code, when I import the graph, it won't run all that other code. Let's make a graph. Let's make an interesting one. How interesting, how fancy should I get here? I just have to give an iterable collection of vertices and an iterable collection of edges. But the edges just have to be pairs. So I could do something pretty wild. Let me do this. All right. Is this too fancy? Is it too fancy? Oh, might be. But here's what I did. I didn't add any vertices. I just sent an empty list. And then I took this string and I split it up into spaces, which means there were strings of length 2, which will be paired, they're iterable. So I think this should run. And if I wanted to look at the neighbors, let's just double check here. If I print a list of neighbors, of, let's say, the vertex A. Oops, this should be parentheses. A. Does it work? No! Totally didn't know what happened here. I think I'm missing a parenthesis, right? Oh, not so bad. Okay, so it says that A is adjacent to B and D, right? Those are the two. Let's see. You see them on the bottom there? Yeah. So A, let's see, I had AB and AD, and those are the only edges with A. Good. Seems right. Let's try B. Let's just double check here. Right, so B is adjacent to D, A, and C. All right. So I made a graph here, and I want to do a search from a particular vertex. So let's try this. I'm going to call my function depth first search. I'm going to call it on this graph G from the vertex. Let's do it from A. And it gives me this dictionary back. Okay, so what is that dictionary? All right, if I look carefully at it, what I see is, all right, it says that A goes to none, and B goes to A, okay, and D goes to B, and C goes to D, a big long chain here, and E goes to D, and F goes to E. Now, is this all of the edges in the graph? That's 1, 2, 3, 4, 5 edges, and I put 1, 2, 3, 4, 5, 6, 7 edges in my graph. So the edges that I didn't come out here there was an edge from A to D. There was also an edge, let's see, B, D, C, D, D, E. Oh, this was supposed to be an F. Sorry. Anything else that I missed? A, B, B, C. Oh, B, C. That's the other one here. Okay. And I think that's all of them. 1, 2, 3, 4, 5, 6, 7. Okay. So those are all the edges right there. The black ones here are the tree. The root is A, right? So it's only parent. It doesn't have a parent. Parent is none. And that's the depth first search tree, right? So it encodes in here paths from every one of these vertices to A. If there was a vertex that was not incident or not connected to A by a path, then it wouldn't show up in this tree. In fact, I can do that right here. If I switch it back to the code for a second, you'll see that if I add 2 new vertices, GH, and I run it again, I actually don't see G or H in the dictionary at all. I may end up with a different tree when I run it again, only because I have the order in which I look at the neighbors. It's because they're in a dictionary, and the dictionary maps to a set. And the set, you can't really rely on the order of the elements in a set to be the same each time you iterate over it, or sorry, each time you run the program. That comes from actually, it's kind of a security thing to try to make it so the average behavior of the dictionary is good. So it's kind of unpredictable, especially with strings, like so someone can't like engineer collisions in the hash table, because they'll be different next time. But the key thing is that G and H are just not here, they're not connected, so it can't find a path. All right, so this kind of seemed like it works. And so that's the basics of depth first search. Now, it's a little weird because you get this tree out, you get this dictionary, but it didn't answer a question that we wanted to answer in the first place. But we can use it to answer a question that matters. So let's pick one. Like, for instance, if I wanted to know if 2 vertices are connected, right? So I want a function that takes a graph and 2 vertices, U and V, and it's going to tell me whether or not there's a path from U to V. This is really easy to do because now I can just check that V is in the depth first search tree from G starting at U, right? So I run DFS in the graph G starting at U, And then I just checked to see if V was one of the keys in there, because if it was, then it's in the tree, and then there's a path. And in fact, I could even pull out that path. Let's check. So for instance, we should assert that in this graph G, A and F are connected. Okay, that's true. And I should also assert, for instance, in this graph that it's not the case that F and G are connected. And I think I've got some missing parenthesis. Good. All right. So that's how you would check if two vertices are connected by a path in the graph, just by using depth first search. And if you wanted to, you can also pull out that path explicitly. And that's kind of a good exercise to do as well. So if I want to just find the path in G from U to V, what I would do is I'd first get the depth first search tree. And the natural way to traverse the path that you get in the depth first search tree is in reverse. That is, it goes from the bottom of the tree up to the root, and if the root was what you wanted to start the path from, I'm actually going to run the depth first search starting from V rather than U. Okay, so I get that tree, and now I'm going to make a path. I really only want to do this if there is a path. So let me just check. If U is in the tree, then we're going to do this. Let's start with an empty list, and I'm just going to loop until I get to U, right? So in fact, the easiest way to do this, I think, is to say, I'm just going to reuse this variable U. Well, it's not none. That is, I'm going to keep updating what U is as I go up the tree, and I'm going to keep adding it to the path. Let's try that. So I'm going to just keep appending it, and then I have to update it. So it's going to be equal to tree of U. And in the end, that's what I want to return, is that path. So maybe this works. Let's see if it works. Let's try it. So print, we called it path of, in the graph G. Let's find a path from, I don't know, let's try B to F. All right. And let's not print the depth first search tree. So here's what it says. It says I can go from B to A to D, D to E, and E to F. And you'll notice that these are all edges, right? AB is an edge, AD is an edge, DE is an edge, and EF is an edge. So that's how I would take the depth first search tree, which is just a dictionary encoding a tree, and I can extract from it explicit paths. And here I return the path just as a list. And so these are two standard uses for depth first search. One, just to check, is there a path? Second is to actually give the path. But depth first search finds its way into a bunch of other data structures as well. Now, if I go over here, let me pull this up again. So if I look at this depth first search tree that I found, it's very tall, right? It actually found these really, it's deep. And that's not a coincidence that it's depth first search, is that it kind of tried to find a longer path before it did any kind of branching. The opposite of this, of course, is breadth first search, where it tries to first look at all the neighbors and then move on to get depth. And breadth first search is actually in some ways more useful, I think, if you are trying to find, for instance, what the shortest path between two vertices is. Depth first search just gives you a path if it exists, but not necessarily the shortest one. In fact, you can kind of see that either of these edges would give shortcuts from A to really any vertex other than B. So let's look at how you get from depth first search to breadth first search. And the idea really now is just that I am going to change the order in which I consider the edges. And before, what I was doing is I was just putting them on the stack, and I wasn't thinking really too much about what order they came back off the stack. But now if I really would like to do all the neighbors, all the neighbors coming out of a vertex first, and then consider everybody else, then as soon as I find all those neighbors, I want to kind of put them, I want to consider them before anything that I discover later. And so this is the opposite of a stack. What I want here is a queue. And it's going to be really easy to implement breadth first search. Given depth first search, we're just going to replace the stack with a queue. Now, I could do this a couple ways. So I think this is kind of a bad thing to do. It makes me really uncomfortable. Is that I can write this breadth first search just using a list again and replacing that append with an insert, where I just sort of insert things at the beginning of the list. Could this possibly work? Well, it gave me a tree, and I think this is probably right. So let's draw it out and see. Oh, you couldn't see the code I was writing. Sorry about that. Here we go. Sorry. Let me bring up the code. It's a problem with doing in-camera editing here. So here's what I did. I copied the depth first search code, and all I did was changed the append in this line right here. I changed append to insert at 0. That's it. And I changed the name from breadth first search, DFS to BFS. And now when I ran it, I got this other tree here at the bottom. You see it. And I will draw you the picture. The picture looks like this. It's got A as before, up to none. A is still the root because I ran it starting from A. It says, okay, B goes to A. Then there's D goes to A. And then C goes to B. E goes to D. And F goes to E. All right. Now, again, it's a tree, probably has the same number of edges as my depth first search tree, 1, 2, 3, 4, 5. And it should be the case that, I missed 2 of the edges, right? There should be 2 edges which are in the graph, but not in the tree, which makes sense because the graph had some cycles. I removed them. I won't draw the one from G and H in here, but let's see. What am I missing? I have, there's an edge from C to D here. And D to A, D to B. Okay, D to B. All right. So these 2 edges. And now here's what's interesting. If I were to kind of use one of these edges instead, I don't get any shorter paths. Right? There's no path that's shorter from C to A than this one that's encoded in the breadth first search tree. Right? It's length 2. I can't do it in one hop, so I need at least 2. Even if I had used this edge and then went up, it's still only length 2. Similarly, this edge from B to D, in fact, that makes paths only longer, right? Because I don't get any closer when I go across this edge. And so, at least in pictures, you could start to feel like maybe you believe this statement that if I build the breadth first search tree, that I'm actually encoding in it not just paths from all the vertices that are connected, but in fact shortest paths. That is the fewest number of edges needed to get from any vertex to the root, which is where you started the search. Right. So that's depth first search and breadth first search. And let me bring up the code again. Right. So very, very similar. Not much to it. This isn't the way you always will see it. Often you will see this done recursively, but like I said, in Python, you've got this hard recursion limit of 1,000. So having a long path of length 1,000 would give you an error if you try to do this recursively. So we just use our own stack, and so this is a straightforward way to both implement them, but also hopefully you see that it's just a slight change in the data structure gives you a different kind of behavior. And both of these are useful. Right now, I feel terrible about this breadth first search code only because inserting at the beginning of a list is hugely inefficient. So if you really wanted to do this, you would implement a queue efficiently. Right? You'd find a queue that you could insert and remove from in constant time and use that instead of just a list like this. But to get the idea across, I think it's all here. That's elementary graph search.